There we discussed about linear independence and dependence, and some problems we have discussed on it. So do you have any queries on that? All right, then let us begin our today's session on basis and dimension, right? So before going to that, just recollect the definition of linear independent set. So whenever we take a set of vectors, all are not equal to 0, we say that the set is linearly independent if whenever you write a linear combination with the vectors such that the result of the combination is nothing but 0 vector, then all the scalars must be equal to 0. So this is the definition of linear independence of a set. Now, if you recollect the concept of vector space, in every vector space you can find a spanning set which is finite. So what is meant by spanning set? It is nothing but whatever the vector or element you consider in the vector space, that can be represented as a linear combination of elements of this set. The very simple example is, if you take the three-dimensional system R cube, x-axis, y-axis, z-axis, whenever you take a 3D point or 3D vector in R cube, that will be easily written as a linear combination of some number into 100 plus some number into 010 plus some number into 001. So in this case, it will be easily observed that x into 100, y into 010, z into 001, where x, y, z are nothing but the real numbers. So typically the set of vectors 100, 010 and 001, we call it as a spanning set for the vector space R cube of R. Not only the elements having 100 model, you can have other vectors also which are also spanning set. The very significance of spanning set is nothing but whatever the vector you take in the vector space, that will be represented as a linear combination of vectors in that set. That is the main significance of spanning set. In the previous class also we have taken one more example, that if we have considered all square matrices of order 2 by 2, whenever you take a 2D matrix, then its spanning set is nothing but the combination of ones and zeros taken 1000, 0100, 0010 and 0001. Using these four matrices, this matrix can be represented as a linear combination. Not only these matrices, you can take other matrices also which can be used as a linear combination. So very significantly we take the combination of ones and zeros, because for every vector space this type of notation you can find very easily. So we can call it as a standard spanning set, a combination of ones and zeros usually we take, right? So any queries for the spanning set? Say, do you have any doubts on this? Right? So whenever you take a vector space which contains a spanning set and the spanning set is finite, means it contains finite number of elements or vectors, you say, that type of vector space we are calling it as finite dimensional vector space. So what is meant by a finite dimensional vector space? A vector space which is having a finite spanning set. So there are some vector spaces having infinite number of elements in the spanning set, which we won't consider here, which is beyond our syllabus discussion, right? So we deal with the finite sets only. Now coming to the definition of basis, if you take a vector space, say V of f, in this you take a subset. If this subset has two properties, the first one is it must be linearly independent, and second one is it spans the vector space V. In other words, if you give a name that the name of this subset as B, then L of B is equal to V. What does it mean? Every vector in the vector space V can be represented as a combination of elements in B. So L of B is nothing but linear span of B is equal to V. Then this set we call it as a basis. So what is meant by a basis? Whenever you take a vector space, in that if you are able to find a subset which is having two properties, one, it spans the vector space and it must be linearly independent. Such type of sets we are calling it as basis. Obviously, whenever you are dealing with the finite dimensional vector spaces, there is a small result that every finite dimensional vector space always has a basis or always contains a basis. So whenever you take a finite dimensional vector space, it always has a basis. So from this, the very definition of finite dimensional vector space is changed as finite dimensional vector space means a vector space which is having finite basis. A vector space which is having finite basis is called as a finite dimensional vector space. And coming to the definition of dimension, since you are able to find a basis, then you count how many values are there or how many elements are there in that set. So the number of elements in the basis, we are calling it as a dimension. So dimension typically a positive number. We can call it as a positive integer. The number of elements in the basis of a vector space, we call it as a dimension. Now, one interesting question is, how many bases will exist for a vector space? So for a finite dimensional vector space, there may be so many bases. So whatever the basis you consider for the vector space, the values in that set are different, but the number of elements in the basis is always equal. Let me say, if I have taken r cube of r, the very power indicates the dimension of the vector space. So since it means 3 means it will has a basis having exactly 3 vectors. Now you can understand that these 3 vectors are linearly independent, because one shortcut technique for verifying whether the set is linearly independent or not, you can make use of the determinant 1 0 0 0 1 0 0 0 1. If you observe that the determinant of this matrix is not equal to 0, whenever the det of the matrix is not equal to 0, it is a linearly independent set. If det equals to 0, it is dependent. So, and you observe that whatever the vector you take in R cube, it is represented as a linear combination of these 3 vectors. So it satisfies the 2 properties, spanning and independence, hence it is a basis for R cube of R. So this type of basis we call it as standard basis. So usually the combination of ones and zeros we call it as a standard basis. Apart from this, if you take any other basis, let me say suppose 1 2 3 3 1 4 2 2 1 or 2 2 5, let me say this is a basis for R cube of R. It is also linearly independent, you can check for the det, and it spans R cube of R. So this is also a basis, you can count that there are exactly 3 vectors in it, hence it becomes a basis for it, right? So whatever the basis you consider, here the vectors are different, here the vectors are different, but the number of elements in the set is same. Here you have exactly 3 vectors, here you have exactly 3 vectors. So the number is fixed. It means that the dimension is fixed, bases may vary. So a vector space may have so many bases. Whatever the basis you consider, the number of elements in each basis is same, but the vectors in each basis may differ. Okay? Any questions to anyone? Please tell. Fine. Now, what is the geometrical significance of this basis? Can a vector space in R cube has dimension 2? Please understand that there is a difference between R cube and vector space in R cube. Let me say, if you have taken that this is R cube, the very power indicates its dimension. It means that it is not possible to find a basis for R cube having less than 3 vectors. So 3 vectors is fixed. If you take any subset in R cube, then it is a subspace. So it may have a basis having only 2 elements, a basis having only 1 element, it is possible. But if you take R cube as a whole, you cannot find a basis having less than 3 vectors. Clear? Right. So if you fix that this is the dimension of the vector space, you cannot find a set which is a basis having less number of vectors, as you mentioned earlier. Right. So if you say that x, you are taking all the values as identical. Is that your notion? So you are saying that I am taking all the values as 1, 1, 1, 2, 2, 2, 3, 3, 3, etc. X belongs to R. Is that your pattern of vectors taken? It means that if you take a value 1, 2, 3, how can you represent 1, 2, 3 as a combination of 1, 1, 1? Is it possible to write 1, 2, 3 as some number into 1, 1, 1? Not only 1, 1, 1, whatever the x you take, is it possible? No. You require one more value. Isn't it? That's it. Not only 1, 2, 3, as far as you are taking different values in R cube, you need different vectors here. The maximum possibility is 3. The maximum possibility is 3. In one way you can say that it is, yes, it is a subspace, exactly. XXX is a subspace. Because the basis for the subspace is nothing but 1, 1, 1. If you consider all the points whose coordinates are identical, it will become a subspace in R cube. It is a part of R cube. And what is the basis for it? 1, 1, 1. Since, yes, its dimension is 1. Since it is only one vector, linear independence by default satisfied. Whenever two vectors are there, you are checking whether they are dependent or independent. If there is only one vector, obviously it is independent. And since there is only one vector which is enough to represent whole space, so it is a basis for it. Since you are using only one vector, its dimension is 1. That's it. Clear now? Let me take the case of xy plane. So what could be its dimension for xy plane? Can you say? Is it 1 or 2? Why? Because typically the pattern of xy plane will be like this. Yes, 1, 0, 0, 1 is the basis for it. And these two are nothing but linearly independent vectors. You cannot write one vector as a multiple of the other. And obviously, every point, please understand, since you are talking about xy plane, it contains 3 coordinates. While writing the basis also, you should take 3 coordinates. You are not talking about 2D, you are talking about 3D. If you are talking about 2D, if you have taken simply xy, in that case you should take 1, 0, 0, 1. This is the basis for it, its dimension is 2. Okay? There is a difference. Whenever you are talking about a vector, you should clearly mention that whether it is 2-dimensional, 3-dimensional or n-dimensional. Based on that, you are going to choose the vectors, the basis pattern. Okay? So, every vector, every point in xy plane will be easily written by using these 2 vectors. Hence, its dimension is 2. Accepted? Any questions over this to anyone? Any more doubts over the point of dimension? So if you talk about the geometrical significance of the basis, it is nothing but if you take R cube, x-axis, y-axis, z-axis is the basis for it. So very simply, x-axis we represent it as 1, 0, 0, y-axis we represent it as 0, 1, 0, and z-axis 0, 0, 1. Not only this, you can find so many bases for R cube. So if you say that there is another set which is having alpha beta, gamma as vectors, and it is also a basis for R cube. It means that you have found a new coordinate system. You have found a new coordinate system in R cube, which are nothing but one axis is alpha, one axis is beta, one axis is gamma. It can just, you can feel it as the transformation of axis you can take. Not only transformation of axis, you have taken three mutually perpendicular vectors. If you observe the pattern, 3D system is nothing but three mutually perpendicular lines congruent at one point. We are calling it as origin, and these three are mutually perpendicular, so that whatever the point you take in the space, that will be represented by means of these three axes. Similarly, I am going to take three mutually perpendicular lines or vectors alpha, beta, gamma, so that whatever the vector I take in R cube, that I am going to represent by means of these three alpha, beta, gamma. So this is also a basis. So basis always defines a new coordinate system if you talk of geometrically, right? Is that clear? That's why if you look at the definition of basis, what you are saying, linearly independent. In one way, they are mutually perpendicular. The other, it spans. What is meant by spanning? Every vector in the whole R cube must be represented as a linear combination. It means that if you take a vector xyz, you are writing it as some number into alpha plus some number into beta plus some into gamma. This is the linear combination. Here also, if you take our regular axis, x-axis, y-axis, z-axis, whatever the point xyz you take in R cube, that you are representing as some number into 100 plus some number into 010 plus some number into 001. Because the coordinates xyz are nothing but taking the perpendicular values on the axis, x-axis, y-axis, z-axis. The same thing you are doing alpha, beta, gamma by means of. So typically there is a specific pattern for finding the linear combination. Clear? That is the geometrical view with regard to the basis. So if I have mentioned that alpha, beta, gamma is a basis for R cube, so whenever you take a vector, that can be represented as a linear combination of this. The scalars obtained here in this combination, we call it as coordinates. So whenever you take a basis, whenever you find a linear combination for a particular vector, in that linear combination, the scalars obtained by you, we are calling it as a specific name, coordinates. So coordinates will vary from basis to basis. If you take the standard basis 100, 010, 001, the coordinates are nothing but by default x, y, z. If you take another basis alpha, beta, gamma, the same x, y, z you take, if you find a linear combination, the scalars will vary. So coordinates will vary from basis to basis. Okay? All of you clear with this notation? Any questions? Right. Then one question haunts our mind, that to check the condition of linear independence, whenever three vectors are given, you simply calculate the determinant. So if the determinant is not equal to 0, the set is linearly independent. If it is 0, the set is dependent. Now let us take the case that I have taken a vector this is my vector. My question is, how can I check that the set is linearly independent? Because if you try to find the determinant, is it possible to find a det here? Say no. So to verify the linear independence, the determinant method is useful only when you get a square matrix. So if you take a 2 vector set, it must be 2D. 2 coordinates must be there. If you take a 3 vector set, it contains only 3 coordinates. In that cases only, the concept of determinant is useful. Whenever you take 3 vectors having 4 coordinates, if you want to check whether it is independent or not, then there are 2 methods available. One, write the linear combination, try to find the values of ABC. Sometimes it is possible, sometimes it is not possible. Apart from this, other technique is you write it as a matrix form. Now apply row operations on this matrix and reduce that into echelon form. Now let me say, after reducing into echelon form, it has the form like this. Now if the last row has become 0 completely, it means that if we have given names as x, y, z, the last row corresponds to the vector z. So z is a dependent vector which is removed by means of applying row operations. So the remaining 2 vectors, whatever the values come here, are linearly independent and they will constitute a basis for the space. So in order to obtain a basis, the technique which we usually follow is write the vectors in the form of a matrix, apply row operations and make it in the form of echelon. Then if the row becomes completely 0, it means that that corresponding vector is removed because it is linearly dependent. Whatever the vectors remain here, they will constitute for a basis. Okay. Whenever you get a 3 by 3 matrix, then obviously we check for determinant. If determinant is not equal to 0, by default it is independent. There is no need to go for echelon form. And we check for the linear spanning. That's it. So if we go with it, I just want to take one problem for you so that you will get an idea. Shall I continue then? All right. Now let us take a sample problem. Now this is the set of vectors I have taken: 2, 2, 1, 2, 1, 1, 2, 1, 0. So my question tag is it a basis for R cube or not? In other words, will it form a basis for R cube or not? If so, we should prove it. So the first thing is just simply find the det. Tell me whether it is 0 or not. Take a moment of time. solve it and give back the reply. So is the debt 0? So if determinant is not equal to 0, it means that it is linearly independent. You can go for the other technique, that apply row operations on it. You cannot make the last row as 0. You can check for that. Not only last row, you cannot make a 0, you cannot make a row completely 0. You can check for the other way around. Agreed? Just try for that. Accepted? Are you getting a row completely 0? No. It is linearly independent. Fine. Now, if you want to prove that it is a basis for R cube, you should check for linear independence as well as spanning. And how to prove the spanning part? It's very easy. You take any arbitrary vector in R cube. X, Y, Z is any arbitrary vector. So what you are going to prove? Whatever the point you consider in R cube, you are able to write it as combination of the three vectors set. So you take that A, B, C are nothing but the scalars which belong to the field such that X, Y, Z is equal to A into 2 to 1 plus B into 2, 1, 1 plus C into 2, 1, 0. So let us solve this. So 2A plus 2B plus 2C, 2A plus B plus C and A plus B. Now you equate the values. Now what happens? You compare the respective values, you solve the equations, then you are going to find the values of ABC in terms of XYZ. So you can find the value of A in terms of XYZ, value of B in terms of XYZ and value of C in terms of XYZ. So you just give me the values for me on solving the equations. So if you simply subtract the first two equations, you will get an equation in BC like that. You can solve on it. So just find those values and give back to me. So C is equal to X minus 2Z by 2. That's fine. I request everyone to try on their own, because this model is important while solving so many problems. I stick on to your solution values, whatever they are. Sometimes you may get some complicated values in the terms of fractions, don't bother. So A is equal to 2y minus x by 2, okay. So 2z minus 2y plus x whole by 2. So let us assume that these values are perfect. So what does it mean? Now let us substitute the values here. So A is nothing but 2y minus x whole by 2 into 2 to 1 and b is nothing but 2z minus 2y plus x by 2 of 2, 1, 1, and c value is x minus 2z by 2 of 2, 1, 0. It means that you have determined the coordinates uniquely. Let me say I have taken a vector 1, 1, 1. So am I able to write 1, 1, 1 using these three values? Yes. You take it as x, y, z, substitute here, you will get a linear combination. So what is the part here? So 2y minus x is nothing but 1 by 2 of 2 to 1. 2z minus 2y plus x by 2. So 1 by 2 into 2, 1, 1. X minus 2z by 2. So minus 1 by 2 of 2, 1, 0. It means that if you simplify these values, you will get 1, 1, 1. Accepted? Yes or no? So you have found a unique expression for the coordinates. It means that every vector x, y, z in R cube, you can write it possibly as a combination of these three values. So the set is a spanning set for R cube. I am saying that whatever the point you take in R cube, say 1, 1, 1, 1, 2, 3, 1, 5, 0, 0, 1, 1, whatever the value you take, you are going to represent it as a linear combination with the set of vectors, because we have found a unique expression. See, by substituting x, y, z values here in this combination, if you simplify the result, you are going to get 1, 1, 1. Yes or no? Let me take other one. Assume that the scalars values are perfect here, given by you. Let me say I have taken another one, say 1, minus 1, 4. Can I write 1, minus 1, 4 as a combination of these three vectors? Yes. How? Take it as x, y, and z. Substitute here. You will get the respective scalars. So 1 minus 1, 4 can be represented as some number into 2 to 1 plus some number into 2, 1, 1 plus some number into 2, 1, 0. So you have found a linear combination for that vector. It is possible for every vector. So the given set is nothing but a spanning set for R cube, because whatever the vector you consider, you are able to write it as a linear combination using these three vectors. Exactly using these three vectors. Okay? I think now you understood what is the meaning of spanning set. The set of vectors will be given in the exam to you. So the question is nothing but he will give a set of vectors and he will ask you that check whether it is a basis or not. So you are checking for the two conditions. So first we go with the linear independence. Second we go with the linear span. If the first condition itself is failed, there is no need to check for the second condition. Because if it satisfies both the conditions only, then only it will become a basis. Okay. If the set fails to satisfy one condition, it is not at all a basis. So you are checking for the two things, linear independence as well as linear spanning. Clear? So earlier we checked for linear independence by doing the determinant method. Now I have checked for spanning by writing a linear combination. There I have represented the scalar values ABC in terms of x, y, z. Now understand one more thing, that if the question specifically asked that if it is a basis, represent 1 minus 1 4 as a linear combination of the basis. In that thing, there is no need to find specific values of ABC. You simply write that 1 minus 1 4 is equal to this combination, solve the equations, get the values of ABC very easily. If you want to find a generalized expression for the scalars, in that case only you need to represent ABC values in terms of x, y, z. If he particularly asked that if the given set is a basis, then represent the vector as a linear combination, then this type of notation is not at all required. Straight away you can solve the equations, get the values of ABC. That's it. So did you get the logic how to prove a basis? Now the same thing is applicable not only for vector points, polynomials, matrices, functions, whatever the case may be, we do the same thing. We check whether they are linearly independent or not, and we check for spanning. That's it. Now here I just want to mention one or two results. The proof is not at all important, the concept is important. So after discussing about the basis, some standard results are derived. However, they are out of our discussion. If you are interested, at the end I will give the proofs for them based on your interest. One thing is, every finite dimensional vector space has a basis, which I mentioned already. Second, basis is the largest linear independent set. It means that, let me say, we have discussed about R cube. So whatever the basis you consider for R cube, it contains exactly 3 vectors. So if you take any set which is having 4 vectors in R cube, then it is not a basis. It becomes linearly dependent. So you can write a set having n number of vectors, but if you simplify the set and make it independent, it contains exactly the number of elements equal to the number of elements in the basis. Okay. So basis is the largest linearly independent set in that vector space. Means if you take a set having more number of elements than basis, it becomes dependent. Clear? The third point is, we call it as basis extension theorem. So what it says, you take a vector space and you take a subset in it which is linearly independent. I repeat again, you take a vector space V of f, in that you take a linearly independent subset. Basis extension theorem says that the set may become basis or it can be extended to form a basis. What is meant by extending a set? Very simple. Let me say my set contains 3 vectors. It is not a basis, but I know that the set is linearly independent. Now for my set having 3 vectors, I will add some more vectors. I will take 4 vectors or 5 vectors. So by adding additional vectors to it, I can make it as a basis. That is called basis extension theorem. So whenever you take linearly independent subset in a vector space, it may become a basis. If it is not a basis, then it can be extended to become a basis. Means by adding some more independent vectors to that set, you can make it as a basis. So that is called basis extension theorem. Another part is, any 2 bases have same number of elements. And then if W is a subspace of V, then dimension of W is less than or equal to dimension of V. That means that for the vector space and the subspace, you find a basis for them. The number of elements here is less than or equal to the number of elements in the main set. It is called basis. It is a result, right? And another one we say, let me say this is my vector space V and I have taken two subspaces here. Now I consider the sum of the subspaces. So for that, if you want to find the dimension, the formula is dimension W1 plus dimension W2 minus dimension of the intersection. So this is very useful formula while solving the problems. I think one or two questions are given earlier over this method. So dimension W1 plus W2 is equal to dimension W1 plus dimension W2 minus dimension of W1 intersection W2. It is just like the formula of set theory you have learned earlier. N of A union B is equal to N of A minus N of B, N of A plus N of B minus N of A intersection B. It is somewhat similar to this. Here it is union, here it is sum. Now the question is, how do we define the sum of the subspaces? That's an interesting thing. How do we define the sum of the subspaces? Whenever you take the sum, whenever you take two subspaces in V, then the sum is defined by set of all alpha 1 plus alpha 2 such that alpha 1 belongs to W1, alpha 2 belongs to W2. It is called linear sum of subspaces. So our discussion is confined to sum of two subspaces only, not for 3, 4, etc. However, in that case only we define the sum in the same manner. So obviously W1 plus W2 is a big set compared to W1 and W2. So W1 is a subset of W1 plus W2 and W2 is a subset of W1 plus W2. Why? Because if you take any vector in W1, let me say I have taken alpha belongs to W1. This alpha can be written as alpha plus 0 vector. So the first part belongs to W1, the second part belongs to W2 because every subspace contains the origin by default. So you can say that this belongs to W1 plus W2. So W1 is a subset of this one. So the sum is always a big set compared to the individual sets. So if you want to find a basis for it, you can find it. And what is the dimension of it? Dimension of W1 plus W2 is equal to this one. This is one useful formula. So please take a note of it. Now let us do some interesting problems. We discuss on that. After noting, please inform. Now, the problem is, I have considered R power 4, the 4D system. 4 coordinates are there. In this, I took two subspaces W1 and W2 as W1 is equal to, I have taken all the 4D points which satisfies the condition whenever I take a 4D point A, B, C, D, it satisfies the condition B minus 2C plus D equal to 0. So whenever I take W2, it contains all 4D points for which the coordinates satisfy the condition A is equal to D and B is equal to 2C. Now, my intention is I want to find the dimensions of W1, W2, W1 intersection W2 and W1 plus W2. It is my intention. So it is nothing but, dimension is nothing but number of elements in the basis. So unless you know the basis, you cannot find the dimension for those sets. So that was the question tag. I think it is one of our previous year questions. So please take a note of it. Then we discuss about that. After noting, please tell. Fine. So first of all, let us find the dimension of W1 first. So if you consider ABCD, so what is the property satisfied by the coordinates in W1? B minus 2C plus D equal to 0. It is nothing but the value of B is equal to 2C minus D. Accepted? Yes or no? Now I will substitute the respective value there. So it is A 2C minus D now if you common the values, because you cannot simplify this further, this point cannot be made simpler. So I have written the coefficients simply. I have taken first coordinate, second coordinate, third coordinate and fourth coordinate. What are the A coefficients? What are the C coefficients? What are the D coefficients? Clear? Now I got three vectors here: 1 0 0 0, 0 2 1 0, 0 minus 1 0 1. What does it mean? Whatever the vector ABCD I take in W1, that can be represented as a linear combination of those three vectors. What are those vectors? 1 0 0 0 is the first vector, 0 2 1 0 is the second vector, 0 minus 1 0 1 is the third vector. So I have written ABCD as a linear combination using those three vectors. So these three vectors are nothing but a spanning set. What is meant by spanning set? You should be able to find a linear combination with that vectors. Since I got a linear combination with those three vectors, it is nothing but a spanning set. Now the question is it independent or not? Right away I say that it is independent. If you have any doubt, you take them as a matrix, you apply row operations, check whether you can make a row 0 completely or not. You cannot make it. Please try. You try and confirm. So by reducing it to echelon form, applying row operations, you cannot make a row completely 0. So it is independent. So there you have proved the spanning. Here you proved the independence. So it is a basis. It satisfies the two properties, linear independence as well as spanning. So it contains three vectors. So the dimension of W1 is nothing but 3. Clear? Any questions, please? Agreed or not agreed? Right. Now let us go for W2. Now I took a vector ABCD in W2. Now whenever you take ABCD, the values of ABCD will satisfy this condition. A is equal to D and B is equal to 2C. So using that, I can write it as A is equal to D, B is equal to 2C. Substituting the respective values here. So if you take the values as common, C 0, 2, 1, 0 plus D you take 1, 0, 0, 1. Accepted? Now you got exactly two vectors. 0, 2, 1, 0 is one vector, 1, 0, 0, 1 is another vector. So whatever the value ABCD you take in W2, that will be represented as a combination using these two vectors. So these two vectors together constitute a spanning set. Now the question is, are they independent or not? They are independent, because whenever you have two vectors, just observe that whether one vector can be represented as a multiple of the other. If it is possible, they become dependent, otherwise they are independent. Since if you observe the positions, this is 0, 0, this is 1, 1. It is not possible to write one vector as a multiple of the other. So they are clearly independent. So these two vectors are nothing but a basis. Hence, dimension of W2 is nothing but 2. Clear? Any questions? Any doubts for anyone? Right. Now, I want to go with the intersection part. So whenever I take a vector ABCD in the intersection, it means that the value belongs to W1 and the value belongs to W2 also. It means that the coordinates A, B, C, D must satisfy the first condition as well as these two conditions. So observing those conditions, we have a pattern here. What is the pattern? From that you have B is equal to 2C minus D, you have A is equal to D and B is equal to 2C. These three conditions must be satisfied by ABCD. So if you substitute the value of B here, which gives that D is equal to 0. Since D is 0, A and D are equal, A is equal to 0. So whenever you take a point in the intersection ABCD, it is nothing but 0, 2C, C, 0. Accepted? So whatever the point you take in the intersection, that is nothing but a linear combination of only one vector, 0, 2, 1, 0. Since it is only one vector, it is by default independent. So it always spans, so it is the basis. So dimension of the intersection is 1. Now you got 3 values. For the last one, W1 plus W2, please understand, you don't know what are the values in W1 plus W2 and what are the conditions satisfied by those set. So you have a straight away formula, dimension of W1 plus W2 is equal to, so applying that, give me the dimension value of W1 plus W2. What it is? 4. So you have solved the problem. Now let us add a small flavor to it. So if I have extended the question like this, what is the geometrical perspective of this problem? W1, W2 intersection W1 plus W2. So in that case, you can think like this. Geometrical perspective is nothing but, since you know the basis, if you draw a picture using that, how it looks like. So if you take the case of W2, it contains 2 vectors as basis. So assume that vector is nothing but a point. So if I have given only 2 points for you, what is the geometric figure you draw? What geometrical figure we draw whenever you have only 2 points on a plain paper? Line. So W2 is nothing but a line. You can see it as a line segment. So what about W1? If I have given 3 points to you, plane, because a plane will be determined by 3 points. Don't misunderstand it. What is the figure I can draw? It is not a figure, because you can see it's a triangle. So we are not talking about geometrical figures, we are talking about the geometrical things, I can say. And whenever there is only 1 point, it is just nothing but a point. Intersection is nothing but a point. So in this way you can say that W1 is a plane, W2 is a line passing through it, you can say it is piercing through it, and the intersection is nothing but a point. Accepted? And W1 plus W2 is nothing but the space containing W1 as well as W2. The line and plane in a space you have considered, that is nothing but W1 plus W2. Clear? Any other questions, please? Any doubts to anyone? Then let me take the other problem. So W1 plus W2 is nothing but a subspace in R power 4 which contains the plane and the line. Just understand like that. The whole space is nothing but R power 4. In that, you have taken a subspace which is containing these two, the plane as well as the line. Now, I took V as vector space of polynomials over R. So I took V, the vector space of polynomials over R. So what is meant by over R? Whenever I write a polynomial, the coefficients in the polynomial are nothing but real numbers. And I considered two subspaces, W1 and W2 in V, which are generated by these sets. So this is the generating set for W1 and the second one is generating set for W2. So generating set is nothing but spanning set. So the first set having 3 polynomials is a spanning set for W1. It means whatever the polynomial you consider in W1, that can be written as a combination using these 3 polynomials. Similarly for W2, whatever the polynomial you consider, that will be represented as a linear combination of using these 3 polynomials. And the objective of the question is nothing but find dimension of W1 plus W2 and dimension of W1 intersection W2. Right? So I will give you the procedure. You just interact with me and solve the problem simultaneously. So for this type of things, we need to write the coefficients as a matrix. So you can take constant term, x coefficient, x square coefficient, x cube coefficient, because that is the maximum power there. So for W1, if you consider 1, 1, 0, minus 1, 1, 2, 3, 0, 2, 3, 3, minus 1. You consider this matrix and reduce it into echelon form, give me the values there. So here, using the generating set, by applying row operations on it, I am getting a basis out of it. Please understand. So generating set is converted into a basis. So since first row will be taken as it is, while applying the row operations, you give me the remaining 2 rows. Yes, one row is 0. I will say that the second row you will get like this and third row you will get completely 0. Accepted? After applying the row operations, you get the result like that. Yes or no? So while applying the row operations, if we have interchanged, it is okay. Always we fix the first row and do the respective things, right? While applying the row operations, we should do R2, R3 based on R1. You cannot make R1 as 0 compared to the others. Right. So it means that, so if you reduce that x cube plus x square minus 1, and from this x square plus 3x plus 1, these 2 polynomials are nothing but basis of W1. Since there are 2 polynomials, dimension of W1 is nothing but 2. So similarly, you go with W2, write the coefficients and give me the dimension by reducing that into echelon form. So are you feeling any difficulty in applying the row operations? I think no. Fine. So go with W2, take the coefficients, apply the row operations and give back the reply. I think for W2 also you will get dimension as 2. One row will become 0 completely. It means that among the 3 polynomials, one polynomial is linearly dependent. You can write it as a linear combination of the remaining 2. Since the third row has become 0, the third polynomial x cube plus 3x square plus 4x minus 3 is nothing but a linear combination of the remaining 2. That's the thing. I think you can observe that. All of you agree? So by getting reply from everyone, I go to the next level. So to find dimension of W1 plus W2 and the intersection, we didn't start the problem yet. Initially you have found dimension of W1 is equal to 2 and W2 is equal to 2 and what are the bases for it. Now here I find the dimension of W1 plus W2 because you don't know what is the generating set for the intersection. If you know the common intersection part from these two, you can specify the dimension of the intersection. Since it is not possible, I want to find the dimension of W1 plus W2. How? You should know a generating set first. From that you can find the basis. So for W1, this is the generating set. For W2, this is the generating set. If you club them together, you will find the generating set for the sum. So I will get a 6 by 4 matrix like this. The first 3 values are taken from the first set. The remaining 3 values are taken from the second set. So 1, 2, 2 minus 2, 2, 3, 2 minus 3, 1, 3, 4 minus 3. So this is the generating set for W1 plus W2. Right? So for this matrix you apply the row operations. Please understand, you fix the first row, make it all these values as 0 first. Then you fix the second diagonal element, then make all these values as 0. You do the row operations like that and give back the reply. Take a minute of time, don't worry. I will give the feedback that do the row operations on your own. I will write the result. Maybe we both are correct. 1, 1, 0 minus 1, 0, 1, 3, 1, 0, 0 minus 1 minus 2, remainings are 0. Provided if we both do the same type of row operations. That could be the matrix you get finally. Check on that. Take your time and do. Yes, it takes time to solve. But is that something different or difficult to get last rows as 0 in applying row operations? No, right. But you get the logic, right? How to solve it? Fine. So the last part is remind that you need to find a dimension of intersection. It's very simple. I have given the formula. Dimension of W1 plus W2 is equal to dimension W1 plus dimension W2 minus dimension of the intersection. So you know the 3 values. You know what is W1, W2 and W1 plus W2 dimensions. So if you substitute the values, you will get the dimension of intersection, which is nothing but 1. So I will say, if you agree with my matrix, the final matrix what I got here, I got 3 rows as non-zero. So the rank of the matrix is nothing but 3. So the dimension is nothing but 3. So if you want to write the dimension, the basis specifically, x cube plus x square minus 1, x square plus 3x plus 1, minus x minus 2. This is the dimension for W1 plus W2, the basis part. So from that, the dimension of the space is nothing but 3. So here you have 3 is equal to 2 plus 2 minus some value. So intersection value is nothing but 1. So in this way, for polynomials we solve. For regular problems, we did the problem already. So here I want to conclude our today's session. Tomorrow we will meet the other topics in this chapter. So can you obey that compared to matrices, is this somewhat easy in solving the problems? Maybe it takes a little time to understand the concepts and fundamentals, but overall solving problems is very easy compared to matrices. Whenever a problem based on Cayley-Hamilton theorem is given, you need to do the lot of calculation like a square, a cube, substitution, make it equivalent to 0, etc. and finding the characteristic equation, but it's very easy to solve. So I prefer my vote towards linear algebra, especially vector spaces. You can check for the weightage over the previous year questions. Many of the questions are posed from the vector spaces part compared to matrices. So you should give preference while your preparation as and when you start. Right? So let us conclude our today's session. Thanks to all, and we will meet in the next session. If you want to add something, you can add. Anybody? So in normal form, if you interchange row, I am not getting lower triangular matrix in right hand side. So you are calling the form of IR00, right? Am I correct? Yeah. So please understand, if you apply the row operations, if you also are saying that whenever you interchange the row and if you perform the operation, you are specifically saying that I am not getting the form like 1 0 0 0 0 1 0 0. This type of thing you are not straight away getting. This one or something is coming in the other place. Am I correct? Say, if you say the first row contains 1, the second row need not be containing 1. So it is very simple. Let me say, suppose you obtain the matrix in this form, say suppose this is your form of the matrix, let me say. Now what happens, you can do the column operation as well as row operation, right? So if you say that C2 and C3 interchanged, C3 is multiplied with -1, then the result will come like this. Then if you interchange the rows, obviously you will get the identity matrix. Accepted? So the only thing is, based on row and column operations, whatever the pattern you can do while applying row and column operations, you can do. Maybe the difference is identity part will come in either of the way. By simply arranging the rows and columns, you get the final matrix. IR00 will come automatically, no doubt at all. But you are able to you are sure that you are getting 1 in any of the part of the matrix, right? That's it. It is enough. You should get 1 0 0 1 1 something, whatever the case may be. You should get an identity matrix, that's all. Any other questions, please? So thank you very much. That's all for today.